All right, we're going to look at the last energy objective, Energy 2.2, and this says to represent and or interpret energy transformations for a phenomenon through a series of pie or bar graphs. So I'm going to give you a couple examples today of this objective, and I'm going to start with this traditional example where I'm just dropping a ball. So if I wanted to draw a series of pie or bar graphs, we're going to look at the ball at the top of the drop, midway through the drop, and then at the bottom of the drop, and we'll say at the bottom of the drop is like just before it hits the ground. So I'm going to draw 3 different pie charts, and this is going to be at the top, this is going to be midway down, and this is going to be at the bottom, and we're going to say just before the ground. Just before ground. Okay, so our first goal here is to figure out what energy was actually involved. And we know that since I was holding the ball up in the air and it was elevated and had some sort of position above zero, we have gravitational potential energy, and we know that the ball was moving, so we have kinetic energy as well. Now, for this particular example, I'm going to ignore air resistance or friction, and I'm just going to take a look at the gravitational potential energy and the kinetic energy. So at the top of the fall, the ball was not moving, so we're looking at 100% gravitational potential energy. That one's easy, not moving, held above the ground at its highest point. Now, midway, I know that I now have half the amount of height, so this one is also pretty easy too. I have 50% gravitational potential energy, and we know that based on the law of conservation of energy that the other 50% has now been transferred into kinetic energy because it was moving. And then finally at the bottom, we're considering that at 0 meters, or at least as close to 0 meters that it's not going to matter. So we're going to call that 100% kinetic energy. So this is just a little scenario here of the standard ball drop at the top, the middle, and the bottom. And you can see how the energy pie charts, the pie itself actually represents the total amount of energy in the system. Since we ignored air resistance, the only 2 energies that we're looking at are gravitational potential and kinetic energy. And you can see how the gravitational potential and kinetic energy transfers and is transformed from start to finish. Now, a cool thing about the pie charts and the bar charts is that they can be interpreted a little bit differently, and that's totally acceptable. Okay, now I'm going to do the exact same scenario, except instead of doing pie, I'm going to do bar graphs, so you can look at the exact same scenario for the ball drop. So I've got the top and the middle and the bottom just before it hits the ground. And then the only difference in the pie charts and the bar charts is that you need to figure out basically how many cubes of energy are we going to use here. So I'm just going to make this real simple, and I'm going to use 4 cubes of energy. So we said at the top of the drop, we simply had 4 total cubes of gravitational potential energy, and we had no kinetic energy. Well, midway down, we had 2 cubes of gravitational potential and 2 cubes of kinetic energy. So we're looking at 50% and 50%. And then at the very end of the scenario, we still had the same 4 cubes of energy, except now they were all kinetic energy and no gravitational potential. So this is the exact same thing as the pies, except now we're looking at bars, and you can see the different variations. They look a little bit different, obviously, and how you organize them looks a little bit different, but the visualization or the representation of the transformation is exactly the same. So you can choose basically which one you like the most and which one's easiest for you to understand. The second part of Energy 2.2 says that equations for work, kinetic energy, and potential energy can be combined with the law of conservation of energy to solve problems. So for example, in the little scenario that we're breaking down here, I could have told you the mass of the ball, the height of the ball, and we know gravity. So you could have actually found the total amount of gravitational potential energy and quantified this, and then transferred that energy throughout the system, knowing that, say this is 98 total joules of energy, half of that energy is gravitational potential and half is kinetic midway, and then all of those 98 joules get transferred into kinetic energy at the bottom. I'm going to take a look at one more example here for you, and we're going to look at thermal energy. Okay, so we're going to look at the car example here, and this is going to help us explain the last two parts of Energy 2.2. The last two parts of Energy 2.2, Part B, says, explain that when energy is transferred from one system to another, some of the energy is transformed into thermal energy. In the ball example, we chose to ignore air resistance and thermal energy. In the car example, we are actually going to include thermal energy because we know that it is present in every scenario unless we're talking about a system within a vacuum. Part C of Energy 2.2 says, explain that since thermal energy involves the random movement of many trillions of subatomic particles, it is less able to be organized to bring about further change. Therefore, even though the total amount of energy remains constant, there's less energy available for us to do useful work. So essentially what that's saying is if there is thermal energy in a scenario, that energy becomes lost from the system itself or dissipated in the environment, and it's no longer usable for that particular scenario. And we are going to do a little example in class with the pendulum to better explain that. So here's my example. Here's my little car, and I'm going to pull this car back. This is a little wind-up toy. And so the very beginning here, we're going to look at the start. We're going to look midway, and then we're going to look at the end when the object is done moving. So what types of energies are involved in this particular scenario? Well, when I pulled the little cart back, since it's considered a wind-up car, we had elastic potential energy. And so I do energy of elastic, or you could just do elastic potential energy. Since I remained on the ground the entire time, then we're not going to be considering any gravitational potential because it doesn't change through without. And then we know that the car was obviously moving, so we're talking about some kinetic energy. So kinetic energy, elastic potential energy. And then there was some thermal energy since the object was in contact with the ground and the ground is opposing it sliding. There's some elastic potential, and there is a little bit of sound too. A lot of the time that thermal energy and sound we lump into one category, and we call that internal energy. So that could include friction, that can include sound, all that good stuff. So at the very beginning, when I'm holding the car back and it's just wound up, I'm looking at 100% of elastic potential energy, and I'll do EL, potential energy. So it's just wound up, it's not in motion, so there's no kinetic energy, and since it's just sitting there wound up, I'm not going to include any internal energy. Now, as the car goes midway, the car is obviously moving. There is still some elastic potential energy because it's wound up. So let's say midway it says has half or 50% of the elastic potential energy. And then I am going to include a sliver, and I'm going to make it pretty small here, of internal energy. Let's say that's 10% of internal energy. And then the remaining 40% is going to be my kinetic energy because it's in motion. Now in the last scenario, I'm at the finish and the car is stopped, so there's no more elastic potential energy. It's not moving, so there's no more kinetic energy. So the only thing that could be left within the system would be 100% internal energy. Meaning the only thing remaining is maybe some thermal energy lost, and we're considering that still a part of the system just so that we can take a look at those energy transformations. Now, the cool thing about the energy transformations and pie charts and bar charts and all that good stuff, you might have said that there's 15% internal energy or 20% internal energy. You might have changed these values, and that's totally acceptable. But what we need to know is that the elastic potential energy decreased across the system, and the kinetic energy, as long as it was moving, might have changed or at least been present. The internal energy increased throughout the system. So as long as we can agree upon that, how you distribute those parts of the pie can be different from person to person. We could do the exact same thing with the bar charts as well, and obviously we just need to determine how many cubes of energy we're talking about and distribute those cubes throughout the system. And a little bit later this week, we're going to be doing a pendulum example, and we'll go through the process of pie charts and bar charts one more time so you can take a look at the different transformations, and we can discuss this a little further. But that wraps up Energy 2.2.